This is Lab 4, Oscillations. The purpose of this lab is to observe and record the motion of a ball connected to a spring that is oscillating, and then use the observed data to create computational models. Using code and GlowScript, I created a projected model of the position versus time data, accounting for gravity and spring force, then compared it with the experimental data. I also used the code in GlowScript to plot a change in type of energy over time graph. Using Hooke's law, we should observe a change in spring force over time as the ball and spring oscillate. Using the energy principle, we should observe no change in total energy of the spring ball system, but as one type of energy increases, kinetic, spring, or gravitational, another should decrease. The result of this lab is to compare the modeled motion with the experimental data to see if there are any discrepancies between the two and to observe how the different types of energies change throughout the oscillation periods. The fundamental physics principles used in this lab include Hooke's law, which is Fs equals negative Ks, and this law was used to find and update the spring force as the ball changed positions. The velocity and position update equations were also used, which are listed here, which is the final velocity equals the initial velocity plus the net force divided by the mass times the change in time, and the position update equation, which is the final position equals the initial position plus the final velocity times the change in time. And we used this to update the ball's position as the net force changed. Next, I used kinetic energy, spring potential energy, and gravitational potential energy, and I used these equations to update the change in type of energy over time and to show that the total energy in the system remained constant. The system can be considered to be the spring, the earth, and the mass, and the surroundings to be everything else. The mass begins with zero initial velocity, taking the fixed point of the spring to be the origin, and an initial position of negative 0.115, negative 0.634, 0 meters. Here are the pieces of coding that I did. And first, I set the initial conditions. So I set ball.m to be 0.402 kilograms, ball.position to be negative 0.115, negative 0.634, 0 meters, the velocity to be 0 meters per second, and then the g, or the gravitational constant, would be 9.8, and then ks would be 6.875, and then the spring length would be 0.127 meters. I calculated S using the formula S equals L minus L naught. I calculated kinetic, gravitational, potential, and spring potential energy. Next, I calculated the gravitational force and the spring force, and then found the net force by adding those two components together. Then I used the velocity update and position update equations to update the ball's velocity and then position. I updated S with the new ball position, and finally I calculated the change in kinetic, gravitational potential, spring potential, and total energy. To the right, we can see these two graphs of the x and y positions. The x positions were very accurate at the beginning, but became less and less accurate as time went on. On the other hand, the y positions remained the same level of accuracy throughout, but did not correctly predict the maximum and minimum values attained. Some errors of this lab may include that the experimental data may differ from the model data because in Tracker, some of the point positions may have been incorrectly placed. The code in GlowScript does not account for air resistance, which could have caused the experimental position data to change less and less over time while the model data remained constant. In conclusion, what does it mean? The energy principle is satisfied because the change in total energy of the system remains constant. Even though individually kinetic, spring, and gravitational energy change, the total energy remains unchanged. The oscillation period is about 0.85 seconds for the x position data, while it is zero point 0.8 seconds for the y position data. We would expect the oscillation period to be similar since one oscillation is dependent on spring length rather than x and y position. That concludes my presentation. Thank you.